We all hear about how self-driving cars are going to make our roads safer, right? But what if their biggest danger isn't a broken part? You know, the old way of thinking about safety was all about finding a faulty component and fixing it. That's basically obsolete now. Today, we're diving into a whole new world. How you make a car safe when every single part is working exactly the way it was designed to.
So, picture this. You're cruising in a self-driving car, maybe on an empty highway at night, and then, bam, it slams on the brakes for no reason. You get it checked out, the mechanics run every diagnostic, and the report comes back completely clean. Nothing is wrong. Every part is working perfectly. No faults, no software bugs, no broken sensors. And get this isn't some sci-fi scenario. It's a real-world puzzle that traditional safety engineering just has no answer for.
And that is exactly where SOTIF comes in. The traditional safety standard, you might have heard of it, ISO 26262, is all about functional safety. Its job is to prevent accidents when things break or malfunction. But SOTIF, or ISO 21448, tackles a totally different beast. It starts from the assumption that everything is working perfectly. Its goal is to manage the built-in, inherent limitations of that perfectly working system.
Right, so how does a car with perfectly good parts go rogue? Well, the answer lies in this one core idea that's really at the heart of the entire SOTF standard.
It's a concept called functional insufficiency. And this is the absolute key to understanding SOTIF. It's what happens when a car's sensors and its software are doing their jobs exactly as they were programmed to, but the program itself, the design, just isn't quite ready for all the weird, messy, complicated stuff the real world throws at it. So the problem isn't a failure, it's not a bug, it's a blind spot in the design's intended function.
To really get our heads around this, we have to look at the actual tech that makes these cars work. Because every single sensor, the eyes and ears of the car, has its own unique built-in weaknesses.
Okay, first up, radar. We think of it as this super reliable thing, right? Sees through fog, rain, no problem. But it has this hidden weakness. When you drive through a tunnel or next to a guardrail, the radar's radio waves can bounce around in strange ways. The sensor, doing its job perfectly, can interpret those weird echoes as a ghost target, an obstacle that just isn't there. And what does the car do? It slams on the brakes to avoid a ghost.
And it's a similar story with cameras. I mean, they see the world just like our eyes do, but they have zero common sense. A camera might see a giant picture of a person on the side of a bus and mistake that 2D image for a real person who's about to walk into traffic. And once again, the system isn't broken. It's working as designed, but the result is another completely unnecessary, hard-stopping emergency brake.
And you'd think LiDAR, the super high-tech laser sensor, would be foolproof, right? Nope. It works by shooting out laser beams and measuring the reflections. But what happens if the laser hits something that doesn't reflect well? Like a car with a really cool matte black paint job or even brand new dark asphalt. The laser pulses just get absorbed, and to the LiDAR, that car or that piece of road is effectively invisible. It's literally a blind spot baked into the laws of physics.
And look, it's not just about the hardware, the sensors. The AI brain itself has these same kinds of limitations. A machine learning model is only as smart as the data you feed it. If you only ever trained it on data from sunny California, it's going to be totally clueless in a Norwegian blizzard. It also has no idea what to do with edge cases, things it's never seen before. A kangaroo hopping across the road? A person lying down in the street? If it wasn't in the training data, the car might not recognize it. Its knowledge is finite.
Okay, so we've got radar seeing ghosts, cameras getting fooled by pictures, LiDAR being blind to black cars, and an AI that's never seen a kangaroo. This sounds kind of terrifying, right? So how on earth do engineers even start to fix this? Well, SOTIF gives them a roadmap, a kind of detective process for finding these hidden dangers one by one.
Well, the whole idea behind SOTF is to take this journey from the unknown to the known. You start in this area of unknown unsafe, which is basically everything that could possibly go wrong that you haven't even thought of yet. Then, through really intense analysis and testing, you drag those potential risks out into the light, turning them into known unsafe problems. And it's only when a risk is known that you can actually build a solution for it, and finally move it over into the known safe column.
But this leads to a really big, almost philosophical question, doesn't it? If these systems have fundamental limits that you can never truly get rid of, how can we ever say they're safe? This is where SOTIF makes a really radical change in how we think about safety.
Because here's the radical idea. The goal isn't perfection anymore. That's just off the table. It's impossible. Instead, the goal is to make the chance of one of these weird things happening so ridiculously, astronomically small that we, as a society, can agree that the risk is acceptable.
We're moving away from wanting absolute perfect certainty and moving towards statistical confidence.
So you've got these two totally different ways of thinking about safety. The old way, systematic safety, was all about being deterministic. You find the root cause of a bug in the code, and you just eliminate it. Problem solved. But probabilistic safety says, hey, you can't eliminate the laws of physics that make a radar wave bounce weirdly. So you can't eliminate the problem, but you can mitigate it. You can reduce the chance of it causing an accident down to an acceptable level.
So what does acceptable even look like in numbers? Well, engineers work with targets like this, 10 to the -7 per hour. Now that's a pretty abstract number, but what it means is you have to design the system so that one of these specific hazardous events happens, on average, less than once every 10 million hours of driving. To put that in perspective, that's like one car driving nonstop 24/7 for more than 1,100 years before you'd expect to see this one specific failure. It's just mind-bogglingly rare.
All right, so that's the high-level theory. We're hunting for risks and trying to make them ridiculously improbable. But how does that actually translate into a real car on a real road? Let's walk through a specific case.
So imagine the engineers have this case file. They've identified a risk. The camera's lane detection can fail. They figure out the specific trigger. It happens when it's really dark and it's raining really hard at the same time. After analyzing the data, they make an official judgment on this specific scenario. Unacceptable. It is now officially a known unsafe condition that has to be fixed.
And because they made that unacceptable judgment, it triggers an immediate action plan. The solution? Add a backup system, like using super detailed HD map data, so the car knows where the lane is even when the camera can't see it. And then, this is the most important part, they have to prove it works. They create specific tests, putting the car in a rain chamber in the dark, recreating those exact trigger conditions. The car only passes if it stays perfectly in its lane. You see how that works? The analysis isn't just a document that sits on a shelf. It creates a direct, testable order for the engineers.
And that really brings us full circle, back to the big question that SOTIF puts right in front of all of us. It gives us this incredible, rigorous engineering process for finding and managing the quirks and limitations of our own technology, but it leaves us, as a society, with a much bigger challenge. The question is no longer, is this car perfectly safe? Because we know it's not. The real question is, how do we decide, together, what's safe enough?